Welcome back, everyone. Today, I wanted to teach you about Goal 5, which is about finding the trigonometric ratios using right triangles. Previously, we learned about our special right triangles. You'll still need to know those for today, so keep that in mind. First, what is a trigonometric ratio or a trig ratio? It's a ratio of two sides in a right triangle. It has to be a right triangle. This does not work unless it's a right triangle. In pre-calc, you'll extend this definition beyond right triangles, but for now, we are only using right triangles. The ratio depends on which angle you're using. You can only find the trig ratios for acute angles, so we'll never ever do this for the right angle. You only look at the acute angles. The first trig ratio is called sine. It's always equal to the opposite side of the angle over the hypotenuse. Next, we have cosine. It's always equal to the adjacent side to the angle over the hypotenuse. And finally, we have tangent. It's always equal to the opposite side of the angle over the adjacent side to the angle. This theta that I'm using here, this always represents an angle measure. It's a Greek letter. And remember, it has to be an acute angle. You always have to put an angle measure after sine, cosine, or tangent to show which side ratio we are using. So for example, if we wanted to find sine B, cosine B, or tangent of B, we're looking at angle B over here. Now the opposite side is the side that does not make the angle. So in this case, the opposite side of angle B is side B. The hypotenuse will be the one across from the right angle. In this case, it's side C, and the adjacent side is the one that makes the angle, but it's not the hypotenuse. So in this case, it's side A. So in order to find the sine of B, we're looking at the opposite side of the angle over the hypotenuse. So it would be side B over side C. Remember, a ratio just means it's a fraction. So we'll keep that as a fraction. Sometimes we'll change it to a decimal. Cosine of B is equal to the adjacent side to that angle over the hypotenuse. So since the adjacent side is A, we would put A over C. The tangent of angle B is equal to the opposite over the adjacent. So it would be side B over side A. We could do the same thing for angle A. We would have to relabel our sides since we're focusing on angle A now. The hypotenuse will stay the same no matter what. However, the opposite side will change, as well as the adjacent side. Remember, opposite's the one that does not create the angle. Adjacent is the one that creates the angle, but it's not the hypotenuse. So based on these labels, we could find sine, cosine, and tangent. It's always helpful to label your angles and your sides based on which angle you're looking at. One helpful way to remember sine, cosine, and tangent, which ratio is which, is by using this word SOHCAHTOA. This stands for sine is the opposite over the hypotenuse, cosine is the adjacent over the hypotenuse, and tangent is opposite over adjacent. So by knowing SOHCAHTOA, you also have to know how to spell it though. You'll be able to remember which ratio is which. The reason these ratios are helpful is because we will be able to find a side of a right triangle when we only have one other side and one angle. Let me give you an example just to practice writing out the ratios. It says express each ratio as a fraction and a decimal to the nearest hundredth. So for A, B, and C, I want you to first notice that we're using angle P for all of them. They always have to have an angle after sine, cosine, or tangent to tell you which angle to use. So we'll highlight angle P. So highlight the angle and label the sides. Across from angle P, the one that does not make angle P is the opposite. Across from the right angle is the hypotenuse. And the side that makes angle P, but it's not the hypotenuse, is the adjacent. So we'll use our trick, SOHCAHTOA. I know sine is opposite over hypotenuse. So for sine of P, I would put 15 over 17 It doesn't reduce, so to change it to a fraction, I'll plug it into my calculator and round to the nearest hundredth. Next, I have cosine of p. I know cosine is the adjacent over the hypotenuse. So it would be 8 over 17. That doesn't reduce, but I can plug it into my calculator to change it to a decimal and round it to the nearest hundredth. Finally, for tangent of p, I know it's the opposite over the adjacent. So I know it would be 15 over 8, and I could plug it into my calculator and get 1.88 as my decimal approximation. Now, once we switch to D, E, and F, notice that the angle switches. Now we are focusing on angle Q. So I want you to either redraw the triangle or erase what you were working with and highlight angle Q. Now, the hypotenuse stays the same. It's still 17. When we highlight angle Q, I see that the side that's not used is RP. RP is the opposite side, and 15 is the adjacent side. Remember, adjacent's the one that makes the angle, but it's not the hypotenuse. Remember the word adjacent, it means next to. It has to be next to the angle. For sine, I'm going to do the opposite over the hypotenuse. So it's going to be 8 over 17. In my calculator, I already did this one. I know that it's 0.47. Notice that cosine and sine switch because when we look at the other acute angle, the adjacent and the opposite had to switch. Next, for cosine of Q, we have the adjacent 15 over the hypotenuse 17. So I'll put 15 over 17. Again, I already did this on my calculator and I know it's 0.88. Finally, for tangent of Q, opposite and adjacent switched from angle P. I know the opposite is 8, the adjacent is 15. Now I'll have to plug this one into my calculator. I don't have this one yet, and I round it to 0.53. Now, what I wanted to tell you is to watch out. If any of these fractions can reduce, you should reduce them before you put your answer. And also, I wanted you to notice the answers that we get for this. Remember, the hypotenuse is always the longest side. So for sine and cosine, the denominator will always be a larger number. If the denominator is a larger number and the numerator is a smaller number, something special happens with these values for sine and cosine. Sine and cosine can never be bigger than 1 because the hypotenuse has to be the longest side. So it's always going to be a smaller number over a larger number. That means that this fraction will always be less than 1 for sine and cosine. Do you think the same is true for tangent? All right, I want you to pause the video and try example 1. Here are the correct answers for example 1, the practice problem. Next, we're going to do example 2 together. It says use a special right triangle to express the tangent of 30 degrees as a fraction and as a decimal to the nearest hundredth. I know my special right triangles are 30, 60, 90, and 45, 45, 90. Since we're looking for the tangent of 30 degrees, I'm going to pick the special triangle that has a 30-degree angle. I already drew it here. You should draw it as well. Now, since I'm looking for tangent of 30 degrees, I'm going to highlight my 30-degree angle. Next, I want to label the sides. The opposite is k, the hypotenuse is 2k, the adjacent is k square root 3. Think so, ka, toa. If I'm looking for the tangent, I know I have to do the opposite over the adjacent. So it's going to be k over k square root 3. K over k square root of 3 can reduce. The k's are a common factor, so they can cancel out. So I get 1 over square root 3. That's a good answer, but it's not a great answer because there's a square root in the denominator. So I need to rationalize it by multiplying by my sneaky 1, and I get square root 3 over 3. So I know the tangent of 30 degrees is equal to square root 3 over 3. And it also said to write this as a fraction and as a decimal to the nearest hundredth. So I'll plug this into my calculator and find that it's equal to 0.58. I want you to try finding the cosine of 45 degrees below. Here's the correct answer. Next, we're going to try a challenge problem. It says, a certain part of a hiking trail slopes upward at about a 5-degree angle. After traveling a horizontal distance of 100 feet along this part of the trail, what would be the change in the hiker's vertical position? So we're looking for x here. What distance has the hiker traveled along the path? We'd be searching for y. So I already drew a diagram. If it doesn't give you a diagram, it's always a good idea to start with that. Now, I only have one side of this triangle. I can't just do Pythagorean theorem to find my missing side. So I have to use a trigonometric function. Highlight the angle that we're given, the 5 degrees. Remember, it has to be an acute angle. Label the sides. Let's start with x is the opposite, 100 is the adjacent, y would be the hypotenuse. Now, I know that I'm going to have to use something that has adjacent in it because that's the side that has a number. It's the side that's given to me. Think SOHCAHTOA. It's up to you whether you want to find x or y first. Let's go ahead and find x first. It's the opposite. So I have opposite adjacent, so I pick tangent. So I'm going to write tangent of 5 degrees equals the opposite over the adjacent. Now, in order to solve for x, I need to multiply both sides by 100 to get x by itself. Now, in order to solve this, I need to use my calculator. So, on your calculator, I want you to first notice whether the top of the screen says radian or degree. Right now, mine says radian. In order to switch it to degrees, since our angles are in degrees, I need to click the mode button. On the third line, switch your calculator into degree mode, hit enter, and you can quit out. So what I'm going to do is I'm going to type 100 tangent of 5. I don't need to type degrees because my calculator is in degree mode. So it automatically knows this is a degree angle. My answer is 8.75 for x. Now, I also want to make sure I use my units. Since this is a word problem, the hiker has traveled approximately 8.75 feet. Next, to figure out how long they've traveled along the path, we're looking for y. So now we are using adjacent and hypotenuse. Adjacent and hypotenuse, think SOHCAHTOA. Which one uses adjacent hypotenuse? That would be cosine. So I'm going to write cosine of 5 degrees equals the adjacent over the hypotenuse. This time, when I multiply by the denominator, I don't quite yet have y by itself. I still have y times cosine of 5 degrees. So to get y by itself, I need to divide both sides by cosine of 5 degrees. Now, type this into your calculator. It's 100.38 approximately. So the hiker has traveled approximately 100.38 feet. All right, finally for the reflection for today. I want you to know, see if you can figure this out. How can you check to make sure your answers for the trig ratios are reasonable? What are the numbers that are possible to plug into the trig functions? Hence, what angles can you plug in? And what are the numbers that are possible to get out of the trig functions? We touched on that a little bit with the ratios. What ratios can come out? It's different for sine and cosine than it is for tangent. See what you can think of. We'll check this next time. We're going to come back to this again, so make sure you're doing your best to understand it. because next we are going to be putting these all towards some special application problems. Talk to you then. Bye.